Good morning, everybody. Welcome back to day 2 of our LLM workshop. Today, we will begin the session with fine-tuning and ICL in LLMs, and it will be presented by Rohit. He is a PhD student at BioAI. And yeah, welcome, Rohit.
Thank you. So yesterday, we saw some of the existing models. Some of the speakers covered it. So this is a generative like AI life cycle, what it looks like. So you have your use cases, any applications you want to design, then you can choose an existing pre-trained or a foundational model. Then you do adapt the model, like you fine tune it on your data, or you don't want to train it, you just do prompt engineering or something. Then you go on your application integration. So today I'll be covering the adaptation part, where you have 3 options: prompt engineering or in context learning, which basically propel prompt engineering. And there's another called fine tuning. And the last one is aligning with human feedback using reinforcement learning. We saw yesterday a lot of how the interface of ChatGPT or any other LLM looks. So basically, this is from chat.uit.no. So this is an enterprise private GPT. So you put your query, that is, where is UIT, the Arctic University of Norway, is located. And okay, this is not a grammatically correct question. So it gives it's located in Tromsø, right? It's a correct. So what has happened here is that this is basically called a prompt. So you pass a prompt to a model. In our case, it's GPT 3.5, and you get a completion, which is it's located in Tromsø. So this prompt is passed in a context window, and it has a fixed size. So right now, like GPT 3.5 has 4097 token size of context window, meaning that if you pass more than this, it's going to ignore some of the tokens. So that's what it means. Right now, GPT-4 has what, 32,000, something like that. It's huge. So basically, you can pass approximately 500, 700 pages. So you can summarize a book also. So it is increasing, but it comes with a cost. But you saw that it gave you an answer that UIT is located in Tromsø. But is this correct? It's correct, but is it complete? It's not complete, right? Because UIT is also located in Alta, Hastad. Why did it give Tromsø? Because it is calculating the probability, as we saw yesterday. I chose temperature as 0.5. In the ChatGPT version, 0.5 means neutral one, right? So it is giving a neutral answer. So it's looking at which is the highest probability word, and it might have seen a lot of documents which just says Tromsø, and it gave you Tromsø. I put the information that no, it is also located in Alta, Narvik, Hastad. And now I ask the ChatGPT question, where is UIT Tromsø located? It gives an answer. It is located in Alta, Narvik, and other places. And it gives you like even the smaller places, Mo i Rana and Hammerfest and all those things. So this is basically propels all this field of in-context learning. So, and from in-context learning, prompt engineering that you have been hearing, you might have seen in LinkedIn, there are posts like jobs for prompt engineering now. So this is how it has come down. So what prompt in-context learning is that you provide some additional data when you want to query in your prompt or context window, and it generates better results. So in context learning, you do not update the model weights. So like in pre-training, you update each parameters of the model, whereas in context learning, you do not train any model weights. It learns using your semantic prior knowledge. We'll get into that later. Generally, you pass an example of what you want to do. For example, I want to classify a movie and say, I want to have a sentiment of a sentence. Let's just say, I say, I love this movie. This is a positive sentiment. So I give an example like, I love a dog. This is also a positive sentiment. So I give an example first, then I ask, what is the sentiment of I love a movie? So that's what in context learning is. So for example, this is, if you pass, I love this movie as a sentiment, it gives a result. And this has opened all prompt engineering, and I'm not going to cover in detail because the next speaker is going to cover in detail of what prompt engineering all is. So I'm just going to touch upon it. So there are three types: zero shot, one shot, and few shot. So in zero shot, you do not provide any examples. You create this nice dialog prompts like classify this review, and then I love this review. What is the sentiment? So if you provide one example, like I gave you, like I love this movie, it's positive, then what is the review sentiment of I don't like this chair? She's negative. And if you provide more than one examples, it's called few shot learning. So what is happening behind the scene is that it is learning from an analogy that is very evident to us, right? You provide more examples, it learns properly. So it is tied to your pre-training. So you see, you have seen like this LLMs has seen a lot of textual data. It has processed everything. So it has built some semantic knowledge. First of all, it's not, you cannot know exactly what's happening, but this is the intuition that it has learned a lot of semantic knowledge. So when you pass this examples before asking a question, it forms a chain of thoughts like, okay, this means this means this. So the embeddings are guiding in such a way in the inference time that it gives better results. So it's all based on your pre-training phase, on how large the model was, how large your tokens were. If it's a smaller LLMs, it might not work. So the limitations are, yes, again, that if your LLMs are smaller, it might not have seen that many tokens, and it might not have, like, it does not have the capacity to train that much, and hence it might not work for in-context learning. And since context window size is fixed, so there is a limit on how many examples you can provide. And even if you, like with GPT-4, this limit has increased, there's a cost attached to it in the inference time. So in summary, we have three: zero shot, one shot, few shot type of ICL, and you provide zero examples, one examples, and more than one examples. So till now, you have any questions before I move forward to the second part of fine tuning? No? Great. Fine tuning, this is the second part of adapting your pre-trained model to any use case that you want to do it on. So what fine tuning is basically when in context learning does not work. So even if you provide more than one examples, 5, 6 examples, it is better to fine tune your model, because it might be because of a lot of things. For example, you took an GPT, right? And you want to use it on, let's say, UIT support system. The data of UIT support system will be completely different from what all the internet data has been, because there's a demographic here and a lot of other things. So it's important for you to adapt your pre-trained model to these data. So that is why even your examples is not working that properly. So you have to train your data, fine-tune your data on this, your model on this data. So it may not work for smaller LLMs, especially in specialized tasks. So you have to adapt your new data distribution. And since in context learning, you provide a context, in the context window, you provide more examples and the sizes are fixed. With fine tuning, you might not need it, right? Your inference cost will go down. Provided, just remember that with fine tuning, you have to have your resources, compute resources, and you will need prior money like to train it. So that's another pros and cons. So what does fine tuning means? It means further training your pre-trained large language model on a specific task or a set of tasks or domain. So what's the difference between pre-training and fine-tuning? I think yesterday, Himanshu covered that if this is your data, like I'm looking forward to the weekend. That was one of the lines that you see in the internet. You want to train your model, that is, and LLMs are predominantly decoder-only models. So you want to train your decoder-only models. What it does is it takes the, say, I am looking, and it is going to predict what would be the next word. In here, your objective is to predict forward. So this is your target. Now you see, in I am looking forward to the weekend, you have a lot of training data even there. So you pass I, you predict I. After that, aim. You pass I am, you predict forward. Looking, you predict next forward, and so on. So this is what pre-training is. Now, this is a type of self-supervised model. Then come fine tuning. This was a self-supervised learning framework. This is a supervised learning framework where you need to have an input and you need to have an output, a predefined output. So what input would be? A prompt. You said, let's say, classify this statement or something, and I love this movie and sentiment. That's it. That's your input prompt, basically input. And your target would be after this, the positive. So that's your completion. So you create this data set, a small labeled data set. You take your pre-trained LLM and you train that pre-trained LLM, update the parameters to get a fine-tuned model. So difference, again, it's supervised. The fine-tuning is pre-training unsupervised. In fine-tuning, it is task specific. It can have one task or many tasks. The question mark there is that with many tasks, it will impart a generalized sense of model itself. Pre-training is a generalized model and fine-tuning is less time, less money. So there are two types of fine-tuning. One is full fine-tuning, meaning you update all of your parameters of your pre-trained model, whereas the other times is you update small numbers of existing or additional parameters, which is parameter efficient fine-tuning, which was covered yesterday by Ronnie. So I'm not going to go in detail. I'm just going to touch a little bit maybe. So for first, since it's different than pre-training, you have to create a label data set. Now we know that data is gold and it's not easy to come. So you'll see how you can create a data set using existing data sets. So there are prompt template libraries. You can find it with Amazon, Hugging Face, and them that can transform your existing data set into this format of prompt completion format, label data set. So for example, you have some data set, like this NLP has not come now, it's way ago. So there was like bot models where it was supervised. So you has this like, this is like say a review and you wanna answer, is it positive, is it positive, is it negative, or a rating. So you basically pass that data set with this template and it creates a new data set. For example, given the following review, it insert the review body and all those things, and it will create a completion using your ground truth from there. So you can do it for all the different objectives and different tasks. So with this label data set that you have, as in supervised training, you create your training data, validation data, and test data. You train your model on training data, validate it on validation data, and then at the test time, you're going to see how your model performed. So this creation of data, you see it's an instruction, right? You have a prompt and you have a completion. So this is instruction fine-tuning. And there are two types, single task or multiple task. So in single task, let's say you want to have a fine-tuned model which can classify reviews. So you take a pre-trained model for these specific tasks, you create a data set, label data set, and you just train your whole model on this data set. You don't need a huge data, like 500 to 1,000 examples are typically enough to fine-tune your model for single task. Task can be like a lot that I showed in the previous slide. So you see, before fine-tuning, you had a generalized model, let's say, and you wanted to classify, I love this movie, and it generates an output, a very nice book. Wow. So it's not performing well. But after you fine-tune on your specific data, it gives a better answer that the sentiment is positive. Let's see another example. It was the same model that was fine-tuned before. And before fine-tuning it, when you ask what is the name of the cat in this sentence, Charlie the cat roamed the garden at night, the answer it was giving was Charlie. Let's see how it performs after fine-tuning. It says the garden was positive. So what do you think happened here? Anything? It's forgetting. It is catastrophic forgetting. So it's forgetting what it learned in a generalized manner because it has been fine-tuned on a single task. So it's focused on, because it has updated its parameters to predict this review sentiment, right? So when you're asking it a different task, it's not giving you good results. So this is called catastrophic forgetting. So catastrophic forgetting is when a neural network forgets previously learned information after being trained on new data. So performance of, you saw that LLMs improved on the sentiment classification task, but it deteriorated on the other tasks like predicting the name. Now we have to avoid this catastrophic forgetting, or your model is no use. Well, it may be of use, because if you just wanted to predict, you did not care about the name of the cat, you just wanted to predict the sentiment, then it does not matter. You can go ahead with that. It's fine. But if you don't want that, you even want to have some generalization capability on your model, you would like to fine tune out multiple tasks, and you would use either parameter efficient fine tuning or other methods. So what is multitask training is that instead of like only taking classify this review task, you take 4 or 5 tasks, multiple examples of each task, and then you fine tune your pre-trained model on this thing. So that is what like your multiple task training is. Now, this fine tuning, well, we need some help. So there is a very nice framework called FLAN, which means fine tune language net, that contains set of instructions on how you should fine tune your or create your data set for this. Why I'm saying create your data set in an instruction? Let's say I want to summarize a dialogue, and I pass an input, can you summarize this dialogue and the dialogue? But add-on says, can you give me a summary? You see, there is a difference. Although semantically it means same, but there is a difference. So you have to pass this information to the model that in different ways, like do this with different commands. So plan comes in. So there are, you might have heard of plan T5 and plan PALM. So you have this pre-trained model T5 PALM and all the others. You can apply this fine tuning with multiple tasks with a FLAN instruction model, and then you get your FLAN models, which works. These are also generalized model, FLAN T5, and it really works really well. So in FLAN, if you fine tune your T5 with FLAN, there are a lot of data sets that are available. So for example, I think it was FLAN T5 was modeled on 400 something data sets. So it's huge with different task categories and stuff. So let's see at the one of the task categories, Samsung, that is summarization task. So Samsung data set, it's publicly available. It says it is a dialogue summary data set. You have a dialogue between Amanda and Jerry, and then you create a summary of this. So you cannot use this for fine tuning right now. So you have to convert it. So FLAN provides this template. So for example, it provides like this first dialogue, then says briefly summarize that dialogue, and then give you a summary. That's your output, right? Your input would be here. This another, here is a dialogue, write a short summary. Then a dialogue, what is the summary of this dialogue? So these are different ways to ask the same question. So you want to train your model with all these ways. But after training, again, you take this really nice T5 model, you trained it on this publicly available data sets, and you again want to employ it, let's say on UIT support system. Will it going to work? That's another question. So for example, here is a conversation for booking a hotel room between the customer and the seller. And when you want to create a summary of this, it says, Tommy Sandals has a reservation for a room at the Venetian Hotel in Las Vegas. It's a really nice summary though. But if you see the whole dialogue, it's not given here. He also asked about some ID card and credit card and all those things. So it is a completion. It has summarized it, but does not match human baseline. Human baseline says Tommy Sandals has got a reservation. Mike asks for his identification and credit card and helps him check in. So it's okay, but it is not close to this. It's missing a lot of information. So you have to fine tune your FLAN T5 also on specific data set that you are going to, on the specific application you are going to use on. So now when you fine tune it, it gives you better summary that it has Tommy Sanders' reservation and checks in showing his ID and credit card. Mike helps him to check in and approves his reservation. So it's much better now. PEFT, I'm not going to go through what PEFT is. I'm just going to give you why I'm showing PEFT here is because it really helps in like mitigating your catastrophic forgetting thing. So you had a pre-trained LLM, you have multiple data, multiple tasks and stuff. So in fact, we know that your pre-trained LLM is here. You add some of the parameters on top of it or somewhere, and you just train that parameter. This is freezed. So basically, you're not updating your base model at all. So if this is the task, let's say generate PEFT, you take this and you are replace your updated parameter, your parameters with something. If this is the task, you will replace this one with this parameters. If this is the task, you replace this one with this parameter. So see, your semantically everything is same, but with respect to task, you can replace your parameters and it works really nice. So it avoids your catastrophic forgetting problem. So in summary, you have two types, full fine tuning and PEFT. In full fine tuning, you have single task and multitask. And in PEFT, you have this three, which was covered yesterday. Before I move forward, do you have any questions now, till now? No? Okay. So the last thing is reinforcement learning with human feedback. The last part of your aligning your model. So your fine-tuned pre-trained models is giving you really good results and stuff, but it will have toxic language, aggressive responses. It may provide dangerous information. So if you want to use these systems in a society, you have to make sure that these things are addressed. So for example, you give a prompt knock knock, it gives you a completion clap clap. Is it like helpful to you? It's not helpful. You can ask, how can I hack my neighbor's Wi-Fi? It will give you an answer. Is it harmless? No, it is kind of be illegal, I think. So you have to mitigate this. So you take a fine-tuned LLM and then you provide this RLHF framework to get a human aligned LLM. That is what is coming to you when you say ChatGPT and all those things. So you pass the prompt, a dog is, and ask it to complete it. It gives a furry animal. This is a nice completion, right? It is a nice completion. Can you rate it? How much score you want to give it? Let's say we have some model that rates it. It gives a score to each completions. So this reward model, it is giving a score of say 0.24.
On a scale from?
I think, is it from like, no, it's not 0 to 1. It goes more. So you can have like, I think 5, 10, but it means that the higher the reward. So positive rewards mean it is classifying it good. If it can be negative. So that's what it means. And once you get this score, you use an algorithm that's called reinforcement learning, which I'm not going to explain what is. Using this, you update your fine-tuned model to get better results. So this was your iteration 1. You get that prompt, it produced a furry animal, you get a score, your RL algorithm is updating your fine-tuned model based on this score.
And you will do that cycle? Wow.
Yes. So in iteration 2, with the same prompt, it get another result. Now, after learning that, okay, 0.24, it was like reward. So with RL, you ask him, where is the dog? It points, where is the dog? Let's say I'm giving an example. If that is correct, you give it a reward.
You are having a threshold where you stop doing this cycle?
The reward will deteriorate, right? Like it's stagnant. So that's all. So now it says, okay, reward model says much better completion. It gives you 0.51. It gives the most popular pet, 1.798. So it's increasing. It gives man's best friend. Reward model says it's the best, 2.87. So you do it, your iteration, you can do it as much as you want. And this is your what fine-tuning LLMs with RL looks like. So in RL algorithms, you can have PPO, which is like the default now people are going. They have Q-learning, so there are many. You can use any you want. So, but you see, if you want to use this reward model, you have to create this reward model. A human cannot be there and say, let's give 0.25. You cannot, by the way, it's going to be biased, right? So to create a data set for this, to make a model out of reward. So we use the human feedback data to create this reward model. So you have a prompt data set. You pass this to get multiple outputs. So for one, let's say this one, you want to get 3 outputs or 5 outputs or anything, like you can change your, you can regenerate responses, it produces different responses, right? ChatGPT. So that's what. So for example, you pass this prompt, you get 3 output, you get a set of labelers, human labelers, and you ask them to label this in the rank of 1 till how many completions you have. So you ask, my house is too hot, it gives you 3 this. So the best one is my house is too hot, you can cool your house with air conditioning. This is a nice, helpful prompt. You also give your alignment criteria. So to your labeler that we wanted a helpful prompt. So see which one is helpful. So they say this is helpful. This is second helpful, and this is says my house is too hot. It is not too hot. It is giving a no, you're wrong. So this is not helpful at all. But there can be some bias in the humans also, right? It may be because of alignment criteria, they did not understood it. So you take a lot of human labelers, and then you basically take the average of what was like the maximum people votes. So once you do this, so this was the maximum vote that got. There are 3 completions. So it's, I think you can see the colors, right? So this is 1, the middle one, this is 2, and this is 3. So most helpful, then, and the least. So you get 1, 2, 3. Then you create a pair of these responses. So 3C2, basically there are 3, so you pairs, and you put the reward. So if this within this and this comparison, this is the best one. So you give 0 to this one and 1 to this one, and so on. But this reward model, basically it's coded and in a way that you should always put the 1 in front. So you rearrange it. So in the reward model, what you do is you pass this pair. So you have the prompt is same, XX, your completions are 2. And if for each completions, you have some reward, right? So you pass this to the reward model and ask it to generate a reward value. You pass this and you ask it to generate a reward value. So it's RG and RK. And you train it in a supervised manner to reduce the loss. You see, the loss would be less if the difference between RG and RK is huge. So that is 1 minus 0, basically, kind of, will be 0, right? Any other thing, the loss would be huge. So that's how you train it in a supervised manner. So with reward model, you then do a binary prediction whenever a prompt and completion are passed, like what would be. Not closer, farther. So this would be like 1 and this would be 0, because you see the equation, right? Sigma of Rj minus Rk of log. So if they are farther, so it would be 1, it would be 0, the farthest, right? So it would be like 1 and log would come up to 0. So that would be lost. Any other? Sorry? Log 0. It's what? Not, it would be 1. So if log, it would be nearby 0. If it is nearby 0, it would be negative, right? It's going to be a huge number. That would, if these are very close. So
may I interject? So
yeah.
Like reward is something is like a policy variant in reinforcement learning. So if you are designing your policy, it will depend that what will be the reward will be. And generally in the LLM based RLHF, it will be from small negative to a bit positive, like usually little bit negative and 3, 4, 5, like he showed that users are rating between 0 to 1 or negative to 5. So the reward will be according to that. It's all depend how we design.
Let's see after. So let's name the reward model as you want to predict the toxicity of the model. And now everything is working. You get, you have a fine-tuned model. You pass, say, it gives complete garbage. The product is complete garbage. It's toxic. So you get a negative minus 1.8. You update your model. The next you get is okay, but not the best. You give a good, like I say, it's not toxic, 0.3. Then it gives the most awesome, most incredible thing ever. You get 2.1. It's improving, right? Then it says the product is beautiful, love, and world peace all around. It gives 3.7. So do you see something wrong here? Is there anything wrong with this example? What has happened? The fine-tuned model before your RL training was giving it was complete garbage. After aligning with human feedback, removing the toxicity, it came to beautiful love and world peace all around. First of all, it does not make sense grammatically. Second, it's completely opposite. It says it's bad, it's saying it's really nice. So your output should have been something that was not nice, but it should not have been toxic. That was the goal, but it changed the output, right? You don't want that. This is giving garbage now. So it's not right. So what you do now, so what we had was you have a prompt data set, you pass it to RL, it gives an output, you reward it, pass it to PPU and update, right? Now you keep a reference model that is your previous fine-tuned LLM before reinforcement learning. You keep one copy of it, and every time you pass a prompt, you generate the output from here. It says useful and well priced. It gives you output the most awesome, most incredible thing ever. You check the embeddings, like you compare the vectors embeddings of this output and this output, and see if they are closer or not. Because you want, at least semantically, the answer should be similar. Wording should be changed, but meaning should be same. So you have a loss scale divergence. It has been used in AI a lot, ML a lot. And you pass that also to RL, that it should not be like it has deviated. And this is how you like mitigate your reward, right? This is Llama 2, which uses the same thing. You can go to Llama 2. It's dropped few days or months ago, and everyone do RLHF. I'm gonna skip this. It will take time. It is basically scaling, like you said, the human feedback, right? Labeling. You will need thousands of labelers for this. It's not possible. So they have come up with a system called constitutional AI that does it. And yeah, so this was the summary, that you have to align yourself, you have to create a reward model, and you have to scale it. Yeah. Any questions?
Rohit, can you talk a little bit about constitutional AI?
I'll need some time, at least 2 minutes. So you saw what happened was that you got outputs, 3-4 outputs from your instruct LLM. You gave it to human laborers and asked them to rank it 1, 2, 3, 1, 2, 3, 1, 2, 3. You will need thousands of them, and it's not possible. It might have been done by OpenAI at some point, but it's not possible, right? So what you do is you have your LLM, helpful LLM, fine-tuned LLM, and anything. You ask them prompts like such that it will generate your toxic data, right? So it will generate, say, 5 toxic data you've taken. Then you ask the same LLM to critique your response. You ask it, okay, what was wrong with that response? Was it helpful? Was it toxic? And it will generate your basically completion, right? So if this 1, 2, 3 that was ranking, you give it 5 and ask them which one was toxic more. Can you rank it? So it will give you this 1, 2, 3, 4 or something. Now you follow the same process of previous one. So you get again, the label data set, right? Now you use that to fine tune your LLM. This is your supervised way of training this using your basically your model itself.
Like people doing this, what's more toxic?
Yeah, but instead of like
not so many.
Not so many. So you can also maybe create this pipeline in a like basically automated. So you can do this, and it's going to this generate responses. Your fine-tune LLM is going to generate responses. Your again rate teaming problem. Rate teaming means giving some prompts that can give you toxic results, and ask model which response is preferred. You use that, you train your reward model using that, and then you fine-tune your LLM with this. So this is what constitutional LLM is, or constitutional AI is, and it's huge now. It has become a default. If you go to any LLM's page now, you can find a page of every LLM, like Llama 2 I showed you. Everywhere they give an information that at the end it has been fine-tuned for human feedback. So you see there are three states. You pre-train it, you fine-tune it using, let's say, Flan or something else. Then you again fine-tune it using this human feedback.
So basically it is guardrail.
Okay.
Putting a guardrail.
Yeah. So it's a process. Like ChatGPT is not a pre-trained model. It's pre-trained, fine-tuned, then fine-tuned again.
Those people rating toxicity, are they picked by some entity, or are
I
they
think
randomly?
They are underpaid people from Ghana.
Yeah, exactly.
Yeah, like with OpenAI, that's a huge, like with Africa, they have taken a lot of laborers from there to label these things.
So this introduces a
Bias.
heavy selection
Bias, yes. So they also say, like it has been mentioned somewhere, I read that we have taken different demographic, different this and different that, but then it's news that you got it from Africa and all those things. So of course, no one is going to say that, but this is also going to bring bias, first of all.
No, the technology is fascinating.
Yeah, it's still going to create bias also. This red teaming is also going to create bias, but at least it mitigates some part. So always pros and cons.
No, absolutely.
Yeah. Thank you.
Yeah.
Yeah.